So, in this lecture we will learn about an algorithm for the 3 SAT problem. So, let us understand what this problem is. So, we are given a Boolean expression with n variables. Okay. So, this Boolean expression is in a particular format. So, let me call the variables as x1, x2 dot 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 xn. Now, I can combine these variables and get a Boolean expression. So, this kind. So, in this expression is an AND of ORs. So, we will call each variable xi or its negation not xi as literals, okay. And then we can combine them by OR. Okay, so, take the OR of 2 or more literals. So, if L1, Lk are literals, if you take OR of them, that is going to be called as a clause with k literals. And our formula is going to be a special type of formula, where we will take the AND of clauses. Okay. So, if you denote each clause by I, so you are taking an AND of these clauses, that is the formula that we are Boolean expression that we are interested in. Now, the question is, does there exist an assignment to the a Boolean assignment to the literals or to the variables that satisfies the expression. Satisfies means when you evaluate the Boolean expression, you should get 1. Okay. And we will look at even special kind of expressions, where each clause will have at most 3 literals, or clauses with exactly 3 literals. Okay. So, this is the kind of problem that we this is the exact problem that we are working with. We have a Boolean expression which is an AND of clauses, and each clause is an OR of exactly 3 literals. And we want to know whether there is a Boolean assignment to the variables which will make all clauses simultaneously true. When all clauses are simultaneously true by some particular assignment, we will call that as a satisfying assignment. Okay. So, this is the problem that we are interested in. Clearly, there are 2 raised to n possible assignments. So, one way would be try out all the 2 raised to n possible assignments, but that will be prohibitively expensive. So, we want to design an algorithm which works faster than just try all possible assignments. We will construct a randomized algorithm which will do that. It will still be an exponential time algorithm. This problem is known to be an NP complete problem. Okay, you can just understand that as this is a problem which is known to be very difficult to solve, and people do not expect that this algorithm will have a polynomial, this problem will have a polynomial time algorithm. Okay, so, we will design a randomized algorithm on the lines of a similar randomized algorithm for 2 SAT. So, 2 SAT is the version where each clause has exactly 2 literals. That problem is known to be polynomial time solvable, but we will design the algorithm for 3 SAT, the randomized algorithm for 3 SAT on the lines of a similar randomized algorithm for 2 SAT. Okay. So, let me just describe the algorithm. So, the input is a 3 SAT expression, let us call it as say 5, okay. And what we will do is choose a random assignment. Okay, and then repeat for, let us say, some number of steps, m steps. So, if the current assignment is not a satisfying assignment, choose an unsatisfied clause and flip a randomly chosen variable in that clause. Then we will check for satisfiability. So, this is being repeated if no satisfying assignment has been found, declare phi to be unsatisfiable. Okay. So, in this step, when you check for satisfiability, if you find a satisfying assignment, we will say declare satisfiable if found, if a satisfying assignment is found. Okay. So, the choice of m is going to be crucial. Okay. So, it is a simple algorithm, choose a random assignment, and then if this random assignment is not satisfiable, it means there is one clause, at least one clause which is not satisfied by the current assignment. So, that clause will have 3 variables inside it, choose one of those variables and flip its value. Okay. So, if the current assignment had assigned 1, then you change it to 0, the current assignment has assigned it 0, change it to 1. Okay. So, you flip the value of a randomly chosen variable in any unsatisfied clause. Okay. So, this is the algorithm that we have in mind. Let us first analyze how good or how bad this algorithm is. So, how many times will we have to repeat this algorithm in order to get a, say a satisfying assignment. Now, one feature of this algorithm is if you take an unsatisfiable expression, if the 3-sat expression was unsatisfiable, this algorithm will always give the correct answer. For a 3-sat expression which is satisfiable, we might find the satisfying assignment only on our lucky day. We want to know what is the probability that it will be our lucky day, or we want to know what is the probability that a satisfiable 3-sat expression will be found to be satisfiable by this algorithm. Okay. And we could increase m in order to increase the probability of success. So, we want to really know the relationship between how many steps should we run this algorithm, so that we will get some success, some significant success probability. Okay. So, in order to analyze this algorithm, let us look at a satisfying assignment. Okay. So, we need to bother only about those inputs which were satisfiable, because on the inputs which were not satisfiable, we are guaranteed that this algorithm will return the correct answer. So, let S be a satisfying or satisfiable expression, satisfying assignment. Now, what we will determine is the probability that exactly this particular satisfying assignment is found by our algorithm. We will bound that. Okay. It is possible that the algorithm, the input has multiple satisfying assignment and one of them is discovered. Okay. But what we will analyze is the probability of the algorithm finding one particular satisfying assignment. Okay. That probability will surely be a lower bound on our success probability. Okay. So, in order to find that probability, what we will do is introduce a stochastic process. Okay. So, let xi denote the number of variables that match S at time I. Okay. So, let us look at this algorithm. So, for the time being, let us say that we will repeat this for an infinite number of steps. Okay. We will never stop the algorithm. Okay. And at any time we will look at how many variables. So, we will define a random variable xi which denotes the number of variables that match S at time I. Of course, there is no way of determining what is xi, because we do not know what the satisfying assignment is. Okay. But that is not a problem, we can just, so this is the random variable that we have defined. Okay. Since there is a satisfying assignment, this xi has some particular value. The moment xi is equal to n, we know that all the variables match S and therefore, it is a satisfying assignment, and therefore, the algorithm would stop when xi equals n. We want to know how many steps will it take for xi to reach the value n. Okay. So, let us set up a chain or a stochastic process where the states are the values that xi can take. Xi can be 0, xi can be 1, xi can be 2, xi can be n. Now, suppose somebody tells us that xi's value is, let us say, j. In the next step, what are the values that xi can take? So, if xi equals j at time, let us say I mean, so xi means value at, so if the value of xi is j, then xi plus 1 can be equal to either j plus 1 or j minus 1. Sorry. Okay, these are the only two values that it can take, because so we are assuming j is not equal to n. If j is not equal to n, then what happens is we are choosing a clause which is not a satisfied clause, and in that we flip one of the variables. Okay. Now, when you flip one variable, that can probably increase or decrease the, so let us say this is a clause, let us say small x1 or x2 or not x3. Okay. So, only j variables match the satisfying assignment, therefore, there is one particular clause which is unsatisfied. In that clause, you look at the values of the variables. Okay. So, let us say this is 1 1 0 or let us say 0 0 So, if this is unsatisfied, then the value of it is one particular value, it cannot have multiple values. So, this is 0 0 1. Now, in S, if you look at the variables, the value of the variables x1, x2 and x3, if they are matching, let us say xi equals, I mean 0 or 1, these two possibilities are there, x2 could also have been 0 or 1, and x3 also belongs to 0 comma 1. But the satisfying assignments would have been, there are 7 satisfying assignments. If we choose x1 and flip it, then of course, sorry. So, let us look at, so this is a scenario that we have at some time, the number of matched variables is j, okay, and j not equal to n. Therefore, the current assignment so matched variables is j. So, current assignment certainly is not matching the satisfying assignment. So, there is one particular, there is at least one particular clause on which it is not a satisfying assignment. I mean, it is not, there is at least one clause on which it is different from S, because if it agreed with S on every particular on every variable, then j would have been n. So, let us look at an unsatisfied clause. So, look at an unsatisfied clause. Okay, and let us say the values assigned to it was a, b and c. We will flip one of these. Okay, so, if you choose b, it becomes b bar, if you choose c, it will be c bar and so on. Now, what happens to the number of variables that match S? Maybe a, I mean in the assignment that we are looking at, we had let us say a bar, b bar and c bar. We know that it is not the case that a bar equals a and b bar equals b and c bar equals c. At least one of them must be different. So, the randomly chosen one is going to be different from S with probability of at least 1/3. So, we can say there is a 1/3 probability that we choose a variable which does not agree with S. Of course, it could be the case that all the three of them disagrees with S. Okay. In that case, if we randomly pick, we will with probability 1 get a variable which does not agree with S. But we can always say that at least 1/3 probability is there, because the assignment that we currently have is not matching with the assignment S on some particular clause. So, there is at least a 1/3 probability. So, if we pick that particular variable and flip it, it is now going to increase the number of variables that agree. So, xj plus xi plus 1 would become j plus 1 in that case. Now, if we were unfortunate and if we picked a variable which did agree with S, then when we flip, we reduce the number of matches. So, in that case, xi plus 1 at the next instance, the value of the random variable is going to be j minus 1. Okay. So, these are the two possible values that xi plus 1 can take if you know that xi plus 1 is equal to xi is equal to j. So, from j it can go to j plus 1 with probability greater than or equal to 1/3, and it could go back to j minus 1 with probability less than or equal to 2/3. In case of 2 SAT, this probabilities would have been half and half. Okay. If you look at the 2 SAT case, the random walk, I mean, you can imagine a random walk on this particular graph, it has a tendency to go forward or backward with equal probabilities, but in this particular setup where we are considering 3 SAT, the graph has a higher tendency to move towards 0. We need to ascertain how much is the success probability, that is, if we walk on this particular graph, what if you do a random walk on this particular graph, what is the probability that you will hit n? When you hit n, it means we have reached the satisfying assignment S. So, let x denote the time taken to reach n on the following graph. Okay. So, if you are at 0, you go to 1 with probability 1, and at any other node, and at n you stay there with probability 1, and at any other node, let us say j, you go forward with probability greater than or equal to 1/3, and you come back with probability less than or equal to 2/3. Okay. So, if you start at some random place inside this particular graph, okay, let us say you start at, so instead of, so this is when you define the random variable x and the time taken to reach n, we also need to specify the starting point. So, let us say starting at j. Okay. So, if you start at the position n, if j equals n, then you will reach in no time, and for the others it is going to depend on the particular structure. Okay. So, we can say that x n is equal to 0, x j is going to depend on, so x j is going to be with probability greater than 1/3, this is going to be equal to 1 plus x j plus 1. Okay. Whatever is the time taken to reach from j plus 1, add 1 to it, that is going to be the value of x j with probability 1/3, and with probability less than 2/3, it is going to be 1 plus x j minus 1. Okay. So, these are the random variables that are involved. Let us compute the expected time to reach n from a starting point j. So, let us compute the expectations of these xi's. The expected number of steps required to reach n starting at j. Now, when these probabilities are not known, this calculation we cannot really do, we can only bound the probabilities. So, instead what we will do is, since we are looking at reaching n, we will define a new random variable y, or a new random walk on which you are going forward with probability So, if you are at some particular node j, you go forward with probability 1/3 and you go backward with probability 2/3. Okay. So, this is a different random process than the one we had discussed, because there we only knew that this probability is at least 1/3 and the reverse probability is at most 2/3. But if you look at this modified one, we can say that since this is a propensity to move forward, I mean it has at least the same tendency as x. I mean, so let us call this as the first random process and this is the second random process. The expected time taken by the second random process to reach n starting at any point is going to be surely greater than the expected time taken in the case of the first random process. Okay. Because this is having a tendency to move forward with probability greater than 1/3, this we are putting it to be exactly 1/3. Okay. So, if we get y, if we get a upper bound on y, okay, we know that we can use that same bound for x as well. If y is shown to be at most, let us say some particular amount t, okay, the expected value of y is t, x value is only going to be the expected value of x is only going to be less than or equal to t, and this is much more easier to analyze than the other one. So, we will analyze this particular random process. So, let h j be the expected number of steps required to reach n starting at j. So, we can write the recurrence relations for these h j's. H 0 is equal to 1 plus h 1 and h j is equal to 1 by 3 into 1 plus h j plus 1, we have taken one step and gone to h j plus 1, that happens with 1/3 probability, plus 2 by 3 into 1 plus h j minus 1, and h n is equal to 0. Okay. So, these are recurrence relations. We can write it as h 0 is equal to 1 plus h 1 and h j minus 1 is equal to 3 h j minus h j plus 1 minus 1 and h n is equal to 0. Okay. So, you can solve this is a linear recurrence system, we can solve it and one can show that h n is approx h 1, okay, starting at 0 or starting at 1, how much time would we take. So, we can verify that h 0 or h is approximately, it is equal to, we can just write it as it is equal to O of 2 raised to n. Okay. We can show that it is going to take this much. It is theta of 2 raised to n. So, you can show that this recurrence solves to something like this. So, if we use this, the number of steps we have to perform, if we use this analysis, the number of iterations that our algorithm will have to do in order to reach a satisfying assignment, the value of m will be 2 raised to n. We could have just tried all possible 2 raised to n assignments, okay, that would have been a deterministic algorithm. So, we are not gaining anything by doing this particular, by following this particular algorithm. But there are a few things that we can change in this algorithm, and that is going to give us better bound than 2 raised to n. In case of 2SAT, this does give wonderful results because we had half probability of going forward and backward. Okay. So, if there was a satisfying assignment, we can say that there is a reasonable chance of, there is a significant chance of hitting the satisfying assignment. Here, since the bias is 1/3 in the forward direction and 2/3 in the backward direction, the tendency of the algorithm is to move away from the satisfying assignment. Okay. So, what is the way out? So, two key things. So, first thing is the algorithm chooses a random assignment. Okay. When it chooses a random assignment, the number of variables which match a satisfying assignment follows the binomial distribution. With expectation equal to n by 2. Okay. If you had chosen each of the variables by tossing a coin, you can expect that the number of variables in the assignment that you have come up with, the initial assignment, it will match roughly 2 raised to n, roughly n by 2 variables. Now, that happens with small probability, but one can say that there is a small but not so insignificant probability that you will start with some assignment which is lot more than n by 2, n by 2 matches. Okay. A match is when our assignment, the randomly chosen assignment, is agreeing with the satisfying assignment on a particular variable. Okay. So, if we randomly choose, although we expect the number of matches to be n by 2, it could be greater than that, and that can happen with a non trivial probability. Okay. So, what we will do is, we will not keep on running the algorithm for long steps, because if we keep running the algorithm for long steps, what happens when you run the algorithm for large number of steps is, it will draw your assignment, your random assignment towards 0 matches with the satisfying assignment. So, instead what we will do is, we will run it for some number of steps, and if it has not hit n, that means if it has not found n matches yet, or if it has not found a satisfying assignment, what we will do is, we will just reset and start with a fresh assignment, okay. And that process we will repeat for many times. So, that will be our modified algorithm. So, let me just write down the modified algorithm. First step is, as say, similar to the earlier one, choose a random assignment, okay, and then repeat for say 3n steps. Okay. In our earlier algorithm, we had run it for m steps, that m now is going to be 3n. Okay. So, what do we repeat? Find an unsatisfied clause and flip, and then check for satisfiability. Okay, and then this entire sequence, so let me say I will add a 0th step, wherein I will restart with a new, okay, so this I will run for, let us say, m steps. Okay. So, there are 2 loops. So, this m we will fix later. So, in each iteration of the outer loop, I will choose a random assignment and try for 3n steps. If it does not succeed in 3n steps, I will again choose another random assignment and then run on that random assignment for 3n steps and keep on doing this. We need to analyze what is the probability that this algorithm succeeds. Okay. So, what is remaining is the analysis of this particular algorithm, how is it better than the other algorithm. Okay. So, what we will do is, we will just analyze the inner loop. Okay, this we will call as the inner loop. Okay. What is the success probability for the inner loop? Okay. If the success probability of the inner loop is q, we need to run the algorithm for 1 by q steps, okay, because this is like a geometric random variable. Each run of the inner loop is independent of the other iterations. Okay. So, we can run it for 1 by q steps, and that will be our algorithm, that 1 by q will be m. So, what we will determine is q, and similar to the earlier thing, what we are interested in is this particular chain from j to j plus 1 with probability 1/3 and to j minus 1 with probability 2/3. So, when you look at this particular chain, we want to know the, so suppose you start at jth position, what is the probability that you will hit n? In fact, instead of starting, calling this index as j, let us call this length as j. Okay. So, assume that the starting permutation or the starting assignment disagrees with S. S is known to be a satisfying assignment. So, the starting assignment disagrees with S on J positions. Okay. So, if we get J forward moves immediately, then we will reach N. The other possibility is we have, so how can we reach N? So, K backward steps and J plus K forward steps. Okay. So, at some point if you have J plus K backward steps and if you have J plus K forward steps and K backward steps, you would have gone J steps forward, okay, and then you would have reached a satisfying assignment. What is the probability of that happening? Okay. So, what we want to determine is if you condition on starting at an initial assignment which has only J positions unmatched with a satisfying assignment S, then what is the probability that we will reach N in 3n steps? Okay. So, we want to compute the probability that we reach N in 3n steps starting at position J. Okay. So, let us call that probability as Qj. So, Qj is certainly greater than, so let us say that out of 3j steps, 2j are forward and j are backward steps. So, 2j forward and j backward. Okay. So, let us just imagine the first 3j moves, as j is less than n, 3j is going to be certainly less than 3n. Let us look at the first 3j moves. In the first 3j moves, what is the probability that 2j of the moves are forward and j moves are backward? Well, that is going to be 3j, choose j. So, these are the moves chosen for the backward move, and once the backward moves have been fixed, the forward moves is going to be the remaining. So, this into forward moves happen with probability 1 by 3 raised to 2j times 2 by 3 raised to j. Okay. So, this quantity here is the probability that in the first 3j moves 2j are forward and j are backward. Okay. And if this event happens, then surely we would have found a satisfying assignment. Okay. So, this probability is a lower bound on the probability that you will find a satisfying assignment starting at position j. So, we will need to estimate how small or large is this. We have to bound this, we have to compute a lower bound for this quantity. So, 3j, choose j into 1 by 3 raised to 2j times 2 by 3 raised to j is the quantity of interest. This is equal to 3j factorial by 2j factorial into j factorial into 1 by 3 raised to 3j and 2 raised to j, and this quantity we need to estimate. We will use Stirling approximation for that. So, if you look at m factorial is approximately m by e raised to m, okay, but we can get a slightly better bound. You can say that m factorial is less than root 2 pi m times this quantity m by e, m divided by e raised to m into 2, okay, and it is greater than root 2 pi m into m by e raised to m. Okay. So, it lies between these two numbers. If you think of this as t, this is 2t. Okay. So, m factorial lies between t and 2t, where t is this particular quantity. Okay. So, 3j factorial divided by 2j factorial into j factorial is what we want to compute, okay, and we want to find a lower bound for that. Okay. So, 3j factorial by 2j factorial into j factorial. The by e we can ignore because the same number of e's comes in the numerator and denominator. So, this we can say is greater than the numerator, we will apply the lower bound, which is root 2 pi times 2j, sorry 3j into 3j raised to 3j by e is what we should have taken, but that by e will cancel out in the numerator and denominators, divided by root 2 pi into 2j into 2j raised to 2j times j raised to j into root 2 pi j. Okay. So, this is going to be equal to, so, under root 2 pi 3j divided by 2 pi 2j 2 pi j times, the j's are going to cancel out. So, we will get 3 raised to 3j into j raised to 3j divided by 2j raised to 2j raised to 2j into j raised to 2j into j raised to j. So, these quantities cancel out. So, I will get this to be equal to root 3 by 4 pi j into 3 raised to 3 by 2 raised to 2 the whole raised to j. Okay. So, this I can write it as some constant divided by root j into 27 by 4 raised to j. Okay. And the additional term, so qj, the additional terms was, so we can plug in those values. So, qj is greater than c by root j into 27 by 4 raised to j into, there was a 1 by 3 raised to 2j and 2 by 3 raised to j, 1 by 3 raised to j into 2 by 3 raised to 2j. Okay. So, this is equal to c by root j into 27 raised to j is 3 raised to 3 j, that cancels out from numerator and denominator. So, what remains is two raised to 2 j divided by sorry, this is 2 raised to j, so we had a mistake, this is raised to 2 j and this quantity is j. So, overall we will get 2 raised to j divided by 4 raised to j. This is equal to c by root j times 2 raised to j. Okay, that is the probability of qj. So, if you start at jth position, we can summarize this as, if we start with j matches, probability of success is greater than qj, qj itself is greater than c by root j times 1 by 2 raised to j. Now, what is the probability that you will get j matches when we randomly choose an assignment? Well, that is again binomial distribution. So, out of n we have 1 by 2 raised to n probability of getting everything correct, and so this is the probability of getting all variables matched, plus if you had to have exactly j matches, then that will be n choose j into 1 by 2 raised to j times 1 by 2 raised to n minus j. Okay, so, this is the probability of getting one match, this is the probability of getting j match. If you get j matches, then the total probability of success would be this summed over all values of j multiplied by qj, and this, when you get all matched, you will get it as 1. So, this sum is the probability of success. The overall probability of success, if you denote it by q, q is going to be greater than or equal to 1 by 2 into 1 plus j going from 1 to n minus 1. Okay, so, yeah, j is the number of mismatches, I mean, so if we think of j as the number of matches, this goes from j equals 0 to n minus 1. Okay. So, this summation, sorry, let us say we had stated j to be the number of mismatches, the number of mismatches. So, this is for when the number of when all variables gets matched, then the number of mismatches is 0. Okay. So, 1 by 2 into 1, and in the other case it will be j equals 1 to mismatch being n. Okay. So, this one can sum it up as summation j equals 0 to n so, this one can sum it up by taking 1 by 2 raised to n outside, 1 plus summation j equals 1 to n, n choose j, these two multiply and give n raised to n into q j. So, q j we can replace it with c by root j into 2 raised to n minus j. Okay. So, this can be thought of as so root j is at most root n. So, 1 by root n times 2 raised to n times c summation j equals 0 to n, n choose j 2 raised to n minus j or 2 raised to minus n. So, this can be written as, so if you take root n and c outside, you can write this as c by root n into 2 raised to n into summation j equals 1 to n, n choose j. So, we just plug in the values 1 by 2 raised to n plus summation j equals 1 to n, n by j, 1 by 2 raised to j and 1 by 2 raised to n minus j, we will get 1 by 2 raised to n into q j is going to be c by root j. So, instead of root j we can say, we can just replace it by root n into 1 by 2 raised to j. Okay. So, here from this we can take 1 by 2 raised to n outside, 1 plus summation j equals 1 to n. So, c by root n is common, n choose j into 1 by 2 raised to j into 1 raised to n minus j. Okay. So, this one can say one can just apply binomial theorem. This is going to be greater than 1 by 2 into 1 plus 1 by 2 raised to n times c by root n. So, if you expand this out, you can compare term by terms and say that it is greater than this. Okay. So, we will get q to be greater than so there is 1 by 2 raised to n also outside, 1 by 2 raised to n into 3 by 2 raised to n times c by root n, which is equal to 3 raised to n or 3 by 4 raised to n into 1 by root n. So, if you had to convert the algorithm by running it multiple times, the success probability of which is only q, you would run it 1 by q times, the number of steps required will be 4 by 3 raised to n into say c root n, okay, or c prime root n. This is the number of steps required. Each step takes, let us say, n as if you assume that each step takes n time units, the total running time is going to be n raised to 3 by 2 into 4 by 3 raised to n times c. Still an exponential algorithm, but it is significantly better than say 2 raised to n. Okay. So, that is the randomized 3-sat algorithm.